Hello again. Welcome to Learn Programming in Java. Reuse.
Now, some courses are going to be very generic and allow you to use command line, all various IDEs. This course is going to focus primarily 100% on IntelliJ. Hey, we don't have a lot of money, so I'm going to recommend some, I think, the best value books out there for you. If you want to follow along with these books in the course, they will align very well. If you're kind of on a shoestring budget, the PDF version of the Java 5 book from Bruce Eckel, great value for the money. It's basically free. You want to get the hardcover edition, that's on Amazon. You can click on the link there. It'll take you to the Amazon website. Okay, once again, I'm Hugo Scavino. A little bit of self-promotion here. I've been doing this for 30 years. I started doing Java since the beta, so it's been a long time. I primarily used what I needed to use to get my job done.
So what are we talking about? We're talking mainly about composition. We're going to talk about why it's a critical design principle. It's used to build complex classes. I use it all the time, so will you. It allows one class to contain a reference to other classes. It enables the creation of more complex data structures. This relationship is a has-a relationship, where one class has a relationship to another class. That other class is a full-blown real class. It's flexible, it allows for encapsulation and reuse. It's almost always used as a preferred design principle over inheritance. It allows for greater flexibility and modularity in code software, which is why we're going to emphasize composition over inheritance. So you may have been expecting inheritance to be a big deal. It is. It's a fundamental OO concept. It's a way to do is-a relationships where you have a superclass and a subclass, and the subclass inherits, gets all the methods, the attributes, the ones that are appropriate, and the relationships from this parent. It allows for flexibility in method overriding and classification, where classification is important. But let's see if that's really as important and as hyped up as it needs to be. Okay, apologies if you were expecting shape or an animal class. Here I have a car, all right, that has an engine and tires. So this is a relationship. My car has a relationship, to an engine and a tire class. The engine and the tire class are straight up real classes, all right? They're not fake classes. They're not less important. They have a relationship to car, and a car has a relationship to these engines. I don't worry too much about one-way or two-way relationships, but primarily they are just one way. My car has a relationship to engine. It knows about engines. It knows about tires. Engines and tires don't really know about cars. That probably makes sense in the real world. But what I also want to point out is that nowadays we instantiate our objects with what they need. That's kind of the dependency injection kind of sneaking into our language. So we want the car to have an engine and an array of tires. So we set it up that way. This is composition, and this is the primary way we do our designs. All right, here is not a classic example of inheritance, but a more practical one. In my businesses, maybe you have a customer, and you have different types of customer. You have a classification of customers. Maybe you have a corporate customer, and that way you see a hierarchy and you can extend customer. So customer has a name and a phone in this world. Maybe it's abstract, but here it's concrete. But my corporate customer has a tax information number or a TIN. So here's what I wanted to point out, that yes, I can extend customer. So I get access to these through gets and sets. All right. Maybe I should have made these protected. I'm not sure. We can fine tune that. But here's one thing I want you to know. Look, I can give my customer the pieces that it needs, the name and the phone, and I can have something for myself. So I don't always have to just be a clone or a simple version, a slightly different version of my customer. I can have more. All right. So here's an example of hierarchy of taking what I have, giving it to my parent, and then extending that, having more information. And this is perfectly fine. And customer hierarchy is a good way to see the world and demonstrate it with Java inheritance specifically. Although we're not going to do UML here, this is very similar to what you would see in a UML diagram. All right, so a customer could have a get name and a get phone. corporate customer has a get tin. Now you may be asking yourself, if you haven't seen one of these before, why don't I have these methods in here? That's because I am a customer. I'm not going to copy, even in the UML diagram, the methods down here. I have to visualize and know that whatever I am, whatever is a relationship I have, means I get these. I don't have to copy them down here, because that would be wrong. Because a corporate customer is a customer and it has this extra method. Okay? So this is the visualization of that. And I just wanted to point out to you that you don't duplicate, you don't copy the methods down to your customer. That's the whole point of the reuse, that they're there for you to have. All right, probably not important after you got the classes all set up, but there is an order of initialization when you do the hierarchy. And just in general, I'm not going to get too specific, but you go from top down. So when you instantiate an object that is made up of, 1, 2, 3, 4 parents, the top gets instantiated first. So your most parent gets initialized, and then you go down. Got to be careful in your constructors that these objects exist and they're not null. You'll find out the hard way if you set it up wrong. But when you have inheritance, you have to keep an eye out and think about the initialization order. Usually it's from top to the bottom. Okay, what are some of the features? Let's talk about the limitations. Java does not support multiple inheritance. It hasn't for a long time, and it never will. And that's kind of a weird thing that happened in C++, and I don't see any languages doing that again, really. It can only extend one superclass, but it can implement multiple interfaces. So that's how Java handles that, and I think that's a better way to approach it. You can at most be one parent, right? I mean, and anything more than that is kind of stretching it, and you have weird possibilities and the whole diamond thing. But you can implement many interfaces. So your hierarchy is set, but what you implement and do can be multiple. That may sound a little contradictory, but that's really the way you need to look at it. Inheritance is a powerful feature, okay? It makes things a little more rigid, and it's harder to change and make your classes more robust over time, which is why we want to limit that. But in terms of interfaces, go nuts. Add the ones that you need. We can have as many of those as we want. Okay, while we're not a course in design patterns, I do want to point out delegation. It's a design technique, okay, where the object relies on another helper to perform specific tasks. All right, this involves delegating responsibility. So you can promote flexibility and reusability this way without the whole hassle of being inheriting from something else, and even without having interfaces, really. So a delegator object can have the task of performing some task, but you delegate how it does it to a whole other class or a whole other engine. All right, you don't have to always necessarily have interfaces in here. You may have different implementations, and behind the scenes you delegate the implementation to something else, but you keep a facade of design that prevents your clients from knowing how you do it, but you are doing something based on another delegated class. Let me show you an example. So you might look at this example and say, what? So what? Big deal. Here's what I want you to see, all right? That when I'm doing something, I could have completely separate engines. This delegate free subscription and delegate paid subscription modules could be a whole different subsystem. You could be buying this one from an open source, and then the paid subscription is a model that you have some SaaS out there. But your clients don't know that. You instantiate, you maybe give it a key and say, hey, this is a subscriber, this is not a subscriber, and then your implementation decides what engine to run. It doesn't always have to, for sure, it does not have to involve inheritance. It doesn't always have to even implement an interface. I mean, this is a design principle where you can hide and should hide the deep bowels of how you do something. And for something that has maybe 1, 2, 3 kind of important engines or complex ways how to implement something, you can delegate how it's done through this kind of design pattern. And it works for me because later on, if you want to change out, maybe you in this example, that everybody is a paid subscription. There's no more frees. Well, you just delete the free one, and then your clients don't know any better, and that's the end. That's the end of that. Their interfaces remain solid, they remain consistent, but your implementation can change. All right, we're going to shift a little bit. Okay, we're going to talk about what I think are some important annotations. The override annotation indicates a method is intended to be overridden. Okay, it serves as a form of documentation and lets the compiler let you know that this has been properly overridden. Okay, so whether it's an interface or inheritance, if the annotation method does not actually override a method, it throws an error or warning. You're going to see that in your compiler. Super important not to ignore your warnings. And here's what I mean about not ignoring your warnings. You may stare at this and you're like, wait a minute. I know object has a toString method and there's this red underline. I don't know why it's mad at me. Maybe I'll ignore it. Maybe some of you already see what the problem is, right? That's the wrong method. So the compiler and the IDE, because of this annotation, can help you out, let you know that that's the wrong interface for whatever reason. Maybe it's the wrong return value, the wrong signature. In this case, it's misspelled. So here is IntelliJ rightfully telling you, hey, listen, when you're using this override method, I'm going to help you out and let you know that this is the wrong method. Okay, I'm going to make this more explicit if you haven't already figured it out. When you're choosing between composition and inheritance, just use composition. All right, that's just really the way to go. There's very little downside for choosing composition, and you don't really regret using composition over inheritance. You do get a lot of regrets the other way around. Okay, you set up yourself with some interfaces, maybe some inheritance, but now let's talk about upcasting and OOP languages, especially the ones like Java. Upcasting refers to the process of converting a subclass, or if you implement an interface, to a supertype. Okay, the Java compiler is responsible for that behavior, and the programmer doesn't have to worry about explicitly casting it to something else. So upcasting, fundamental principle, it allows a subclass object to be treated as if it were an instance of the superclass. That's both for interfaces and for hierarchy. Okay, this is not just meant for inheritance. It's commonly used in polymorphism, where a superclass references is used to refer to a subclass, but not always. It can also be in interfaces. And let's see an example of that. Okay, here the shape manager class has a draw method that takes in an array of rectangles. So we can create an array of rectangles. What are rectangles? Well, you can certainly pass in a rectangle. What about a square? A square is a rectangle. It's a special kind of rectangle. So if you're programming to an interface, which is what we want to do, then your little draw method only needs what a rectangle interface and a square, what a rectangle interface can provide. Okay, and the square will suffice. Okay, some abstract shape won't. But here's what I want you to look at, and this is what I think is great about object-oriented programming. Here's the interface. So I don't have a draw for squares, and I don't have a draw for rectangles. I just have rectangle because I know that I can pass it a square. Okay? So look at this. My interface is an array of rectangles. A square is a rectangle. Trust me if it is, if you forget. So here's my rectangle 1 can go in the 0 position, and here's square. Even though I don't have an array of squares, I can pass an array of one rectangle and one square to my draw method, because my draw method it's like, look, I'm perfectly happy with a bunch of rectangles. All right. So this is the way to upcast. All right. You don't have to tell the compilers like, hey, the square is also a rectangle. It's like, yeah, I know. Don't worry about it. I got you. So the draw method can just be based on rectangles, and you can give it anything that is a rectangle. A square is a rectangle, trust me. So as long as you pass it in something that it expects, the language will upcast for you. Now your question might have been, wait, but how is that doing that? I saw that the interface over here is rectangle, but I mean, won't it need to know that it's a square? No. No, it won't need to know it's a square. Because, listen, I got enough. I can get the height and the width from you. I don't need to know that you're a square to do these things. So when I draw, I promise you that all I need is your rectangle-ness to draw. Okay, so here's my little algorithm. Don't worry about the algorithm. But in this interface, in this contract, listen, I just need a rectangle. As long as you give me a rectangle, whether it's an actual rectangle or a square, I can do the drawing. I don't have to know which type you are, because here the language can take in a rectangle or an array of rectangles, and it'll just be fine. It doesn't need to know that it's a square. And that's where you get with upcasting, and that is a powerful feature of the language, is that you define your interfaces at the level that's your least amount of knowledge in order to get the job done. All right, you might be on a hiring interview and someone's going to ask you, tell me about the final keyword in Java. I didn't know where to put this, but this at the end of this chapter seems just as good as any other ones. So let's talk about final. All right, so you can use final in lots of different places. You can have final fields, you can have final methods, and you can even have final classes. All right, a final field is a field that cannot be changed once it's been instantiated. Okay, once it's been initialized, that's it. That's the value that it gets for its whole lifetime. Okay, they're declared within the class, but outside of any method. Okay, they can only be assigned once, either directly or indirectly, and I'll show you that. All right, declared with both static and final keywords. So you can be both final and static. All right, those two things are different. So I can have a value that's final, let's say 42, and if I'm static, then that means that that 42 is available to all my classes and not just my class. So final means I can't be changed anymore. All right, here are two examples how to do set up the final. Now, my first example class, I just set it to 42. All right, I mean, I'm the one in control of the class, so I create the class, and that final int number, it's always 42. So it's initialized by me as some magical number. All right, and it can't be changed. When you instantiate the example class on this top one over here, it's just going to be 42. Now, the other example class, maybe the preferred way is like, listen, you tell me what final is, and then from that point on, it always will be that. So if you create me with 42, then I promise that this will always be 42 for the entire existence of that class. You're wondering now, whoa, how are you doing that? How is this compiling? Notice that there's no arg constructor in here. So the only constructor is the one that takes in this number. So the compiler's okay for deferring to knowing what that final is, but I'm not going to let you create it unless you give me the number, because you put final in here. So if you accidentally put the no arg constructor back in here, the compiler is going to get mad at you and say, no, listen, this final is here. I need to know what the number is before I instantiate you. I can't create an empty no arg version of me and have final. So these things go hand in hand. If I have final, then I can't have a no arg constructor, and one of my constructors needs to initialize this in the constructor. Okay, what about this static final that you mentioned? All right, here's a good example. Here's some math constants. All right, I don't want it to change. Pi is this. Okay, I know it's a lot more. And this E, I know it's a lot more, but for now, let's just, humor me over here. But I also don't want each class to have a final of pi and a final of E. Okay, I want everybody to share the same pi. As I have a public class, I made this public. So look at this, fancy me. I have a public double that gets shared amongst all the class instances. So it's at the class level, not at the object level. Final, which means it's always going to be this number. So that's a lot of keywords. Let it sink in. But here's one way to put those concepts together. All right, what about final in a reference like a list? What if I made the list final? Does that mean I can't add to it? No, it doesn't. It means you can't null it out or change it or assign it to something else. But the final field is an object reference. The reference itself cannot change, but the object's contents can still be modified, adding and removing from the list. So just because names is final, that means you can't make names equal some other array list. But the existing array list you can add and remove to it. Here's another use of final. You don't see it a lot, but do with it what you want. A final method argument over here that means that the method will not change the reference to the object, but the context and fields may change. Remember that from last time? So this rectangle, I promise not to mess with it, but I can set its attributes if I need to. Okay, so I'm not going to change the reference to the object, but its contents may change by putting the final over here. But wait, there's more? Yeah, you can do a final method. Final method is a method declared with a final keyword. So you can't override that method. Remember all that stuff we talked about, inheritance and hierarchies and all that? When you set a method to be final, you can't subclass from it, you can't extend it, you can't do something more to that. That's the end of that method. So it prevents modifications, and it's really good for security. You don't use it a lot, but I thought I mentioned it that you can make methods final. That means they can't be subclassed. Okay, along those same lines, you can make an entire class final. That means you can't subclass from that class. So this is the one and only tire. You can't make any more subclasses. You can't make like a big old tire or a small tire. You just get tire. Usually you find this in frameworks. For security reasons, you just don't want people implementing your own version of this. Think about the string class in Java. That is final. You can't make your own string class. So usually for frameworks, but I thought I'd mention it. Okay, that was a potpourri of stuff, but let's summarize. We like composition. It's a critical design principle, and it shows the has a relationship. A rectangle has a coordinate, a car has a tire. Okay, there's lots of relationships, and those are the ones that we're going to favor. We like that. It's core to our design work. We do have inheritance. Usually you see that in a lot of frameworks. Is it in your code? Maybe. Do you need it? Ask yourself, do you have a hierarchy? Is it important to model that hierarchy with inheritance in Java? If so, great. If not, maybe you don't need it. We loved the upcasting. We always make our interfaces to be at the ones that we need, where we can have it as abstract as possible. That way, if we have implementations of that, either through interfaces or through inheritance, we can just program at the interface level, and we can have something like this, an array of rectangles, which actually includes a square. So in your job interview, someone asks you about final, you can say final methods, final classes, final fields, and you can be all smarty pants about that. So lots of ways to have something called final. So that's it for reuse. There was a lot there. I hope you enjoyed it, and let's go to the next subject.